So welcome everybody and welcome to a new semester. I hope the semester started the best possible way. So I wanted to give you first a kind of introduction about practicalities, where you find all the material. And all lectures will be recorded, and I will have Zoom sessions because we have people who cannot be here physically. And also let me know if there's something, if my English is unclear. I tend to have a very Latinized English. So if there are words you don't recognize, don't hesitate to ask what it means. And the first entry point is what we might call the official website. And if you go to the official website, then obviously you choose the right semester. You will also see here that there is a basic description, and you've probably seen this before. So we will have 4 lectures and 2 exercise sessions. The exercise sessions will not be recorded. And there is actually a very funny thing. So I complain about this every year to the central information system entity which we have. Sometimes it pops up in English if you click on English here, but sometimes it does not. So this has been a recurring error for 25 years. Generation. I shouldn't say more. I won't say more. Anyway, if you look into here, you have a schedule. And in the schedule, if you just look into it, what you will see typically is that I post every week. I'm going to post here the plans which we are going to discuss. You will find weekly lecture material as a PDF, but I will normally only follow partly the PDF file or the slides, because I prefer using my Blackboard, which is actually my whiteboard. So the lectures will always be updated and placed online as a PDF, so you can access my handwritten notes. And you see this kind of room which we have is not optimal, because normally I like to use the Blackboard, but when I use the screen here, then it covers the Blackboard. So that's why I use essentially the whiteboard, and it also gives me much more flexibility. Welcome, by the way. So this was a little bit about the official website. And if you scroll down, so we're going to use Canvas for handing in the midterm exams. There are going to be 2 midterm exams, and they count 25%. And depending on how many we are at the end, we may have either a written or an oral examination. So that depends on if we are more than 10 people, then we will tend to offer a written exam. But this is something we can discuss. So and that's essentially because if we have 15, 16 people, we will often have 3 days, and it's difficult to lock a external examiner for 3 days before the semester break starts. So that's something which we will see how things develop. The messages which you find here are those which you will also find on Canvas, and you will also get them as a weekly email. So that means that you have 3 sources of information about the messages in case you have not registered yet. Because if you haven't registered yet, you will probably not have received an email via Canvas. So that's my official information channel. This is one of them, and then you have through Canvas as well. So Cecilia is going to meet us in the break. She's a postdoc. She's a specialist on spin systems. And she is going to both teach and also do exercises. The essential part is actually the GitHub address, and that's where you find all the information. You can take this information, just download it and use it as you want. So let me just direct you to the website, to the GitHub site. No, that was another site. This one. This is the website which we use. And it actually contains information from 3 different courses. So don't be intimidated by the length of the textbook. The doc folder is the one which is important here. And if you go into the weekly material, you will find some of the slides which you will see pretty soon. So you will get this roughly 1 week ahead. So I will typically finalize them by Sunday, Monday, and then you will get an email with a weekly update, what we are going to do. And then you can look at this week 34 or week 35 or whatever, and that will roughly tell you what we are going to do. And I like to put in questions for you to discuss. There are obviously answers to the questions. Don't look at the answers first, just look at the question. Then, for the computational aficionados, there is a Jupyter notebook where we can illustrate things further. So I will jump between these and the whiteboard, blackboard, or the whiteboard. And that's roughly where you find all information. And you know that is everybody familiar with this kind of version control software like Git, providers like GitHub, GitLab? So you know that you can now just pull down everything here and just put it on your laptops and use it as your own teaching material. Now, one thing which I have provided as well, so I have my own textbook, which is the one I use, and the slides which you find, the weekly slides, are actually extracts from the chapters. And you will get some kind of reading suggestions for every week. That is the lecture book. But you will also find the programs if you want to look into the programs for every single thing which is reported. Every figure has a program behind it. So you can look up these Python programs. If you don't want to use this one, there is a Jupyter book, which you can use. So if you go to the build here and HTML, and you click on the index, you will actually have to be a little bit careful when you display it, because on GitHub, you don't display immediately. So normally, I would recommend just downloading it on your laptop and starting that file from your lab. But that gives you, if you then go back a little bit, that folder has a Jupyter book, as you can see here, for every single chapter. So these are the different, actually named after the topics here. And if you then look at linear algebra, which is the first chapter, there you will find the Jupyter notebook and the notes, which are also in the PDF file. But there you can run the codes as well. If you don't want to look at the individual programs. Does that sound okay? I mean, you're probably going to ask these questions again and again because there's a lot of information. But feel free to use this information as you want. Many people actually take these notes and adapt them to their own lecture notes. So feel free to do that. So all the material is for you at your disposal. Just use it as you want. Any questions so far? Sound okay? So this is roughly the kind of layout. And for those of you who follow the course on machine learning, you will probably see exactly the same layout. And there are some textbooks. So the literature here, and by some funny reasons, these textbooks just ended up here. Some of them out of print, and you will not be able to get them unless you can find them at the library. That's why some of them actually appear here as PDFs, and some of them, they just ended up being there. So Shavit and Bartlett is one of them. And then there is a very good textbooks, which for those of you doing quantum chemistry is a very popular textbook, is Sabo and Oslo. And what you will see is that together with the reading suggestions from my own textbook, you will see reading suggestions from some of these textbooks. So you should have access to the PDF file. So you don't need to buy them because some of them are out of print and some of them are quite expensive. So because it's a limited print, so they are typically in the order of thousands of Norwegian kroner, some of them. But we have the PDFs. So that's where you find additional literature on additional textbooks. Then we are going to put the midterms here. The exercises are actually included in the weekly slides, but you will also find them in the lecture book. And if you go to chapter 1 here, there is a weekly exercise for week 34, which is essentially a linear algebra reminder. So I hope you don't get offended, but many of you are probably taking linear algebra 2 to 3 years ago. And as I said in the machine learning course, if you are like me, after you've done the exam, you don't remember anything. Okay, so this is where we start, because quantum mechanics, the way we are going to teach it, is very much linear algebra based. And you will see that many of the first methods are actually essentially us using different linear algebra methods. Okay, so if you haven't done much quantum mechanics, we've actually had people who've taken this course without having taken a basic course in quantum mechanics. But if you're strong in linear algebra, you can actually, after you go through all this kind of physics jargon, which I will fill in rather quickly. It takes some time to get through the jargon, but if you stay on track with the linear algebra, you can then see what kind of equations we are going to solve. Okay. So there was something else I wanted to say here. No, I don't think so. The first weekly or midterm, which counts 25%, is something which we wanted to present in the around the middle of October or before, in the beginning to the middle of October. And you typically have something like a week to, so this is a take-home midterm exam. It's basically paper and pencil, but it has also, sometimes we may put in some numerical things, but you will find the numerical suggestions through all the programs which are online. And then we have the next one, which we typically tend to present in the middle of November. And then we have, they have scheduled, if you're going to do a written exam, that's December the 10th. If we do an oral exam, we will probably have it in the week after. So that will be the last week, really the last week of the semester, which is normally I think week 50. So our last lecture is in the end of November. Okay. Any questions? Things which are unclear? Okay. So as I said, all the lectures are being recorded. So what I'm going to do now is to switch to the slides, and I'm going to jump a little bit back and forth between the slides and my handwritten notes, just to break the monotony. Okay, so let's just do that. Now I need to find the slides here. So the lookalike of these weekly slides, let me just change it so that everybody can see the full screen. So you will get these slides at the latest at Monday, the week when we are going to discuss them. So you should have them some few days beforehand. And you can see typically the type of layout and the type of topics which we will cover. So I promise there's going to be a kind of repetition of linear algebra and some basic elements, which we are going to see again and again and again. And we are going to look at also, if we get time, at Hamiltonians and basis sets. And then we will essentially stay with fermionic systems. That means spin half particles. We will most likely not do much about bosons. So the main emphasis, depending on your interest, and this is something which we want to map out during the breaks. So what is your background and what kind of scientific interest do you have? There are always somebody who does bosonic systems. But in general, what we've had is that most of the people are interested in, let's say, systems from atoms, molecules, condensed matter physics, nuclear physics, and also other fields, quantum computing, etc. I should also say that the way this course is made is actually a kind of input to a later course in quantum technologies and quantum computing. So you will see many of the things here when you look at it in a more abstract way. These are things which you can immediately reuse if you're looking at a course in quantum computing. And sometimes I will bring up connections between that. And you will see in the notes here, links to many-body physics, links to quantum computing. Because if I now take this kind of heavily biased physicist arrogant attitude, I should say that when you look at quantum computing, one of the big challenges now is actually to understand how to prepare the initial system of a quantum computing system. And to prepare the initial system, the state of the system, this is actually what this course deals about, to understand how you deal with that. So it's an essential element for moving on when you look at the many body systems, because when we are thinking of many qubits in quantum computing, what we're actually doing is that we are physically manipulating a physical system. And this is essentially what this course deals about. And we are mainly going to stay with time-independent approaches. But if there is an interest, we can also discuss time-dependent theories. That's also possible. Any questions so far? So you will often hear me bringing in connections to quantum computing and other fields as well. So as I said, I mean, I'm going to jump a little bit between whiteboard and slides, but sometimes we will have some questions, and you will typically see a question like this one. So we need a small break, because I mean, you guys seem already to be very patient. If you're like me, my attention span is roughly 5 minutes, and then I start daydreaming. But so this is just to break the monotony a little bit, okay? So this is a typical question which you will encounter, and this deals with a reminder about linear algebra. And you will also find this companion notebook, which shows several numerical examples based on these kind of small questions. So I just invite you to take a look at these small things here. I mean, I don't cover everything in the lectures. That's why you get typically the weekly material a little bit ahead of time, so you can go through it and see if there are things you find interesting, if you have questions, etc. And then the exercise sessions, which we have, I mean, the exercises are not graded. You don't need to hand them in. They are normally on the lighter side, but we invite you to be there and discuss with us, because there are many things we can deepen. So this is a typical course where it takes some time to get the insights about the connections between the mathematics and the physics. So this is a typical answer, which you will find. So I'm just giving you the answer. So just as an example, so this is the first of many places where a property of ordinary vectors becomes a statement about quantum states. The norm of a state is real, and the probability is given like that. So this is just a typical reminder. So the first lecture is a little bit about, I just wanted to say a little bit. The lectures aim at giving introduction to the quantum mechanics of many body systems. And these are methods which are relevant for incredibly many fields. So this is a general, all-around theoretical advanced quantum mechanics course. And I obviously have some biases, because I've invested roughly 40 years of my life on quantum mechanical many body systems. And I think it's a considerable challenge in that normally no exact solution can be found. So all the methods you're going to hear about in this course, they are ways to approximate the exact solution which you cannot get. So when somebody says that my method is much better than your method, then you should be very suspicious, because all the methods have their pros and cons. Some of them are good for getting many states and looking at transition probabilities. Other ones are just best for just the ground state of the system. Some methods are very good for time evolution, etc., etc. And some have series approximations which can only be applied in case the particles interact weakly. So a word you're going to hear many, many times here is quantum mechanical correlations. And there are many types of these. So one sentence summary of this semester. The many-body problem is linear algebra in a space that is exponentially large. And every method we study is a strategy for not having to look at all of it. So in a sense, if you do science, this is irrespective of scientific discipline. It's all about finding the effective degrees of freedom. So if you're doing neuroscience, you don't want to simulate the DNA by starting with an atomistic simulation of all the atoms and the electrons. You would never get anywhere. But you would start with a gross simplification by assuming that you have large components which can interact in a simpler way through ordinary differential equations. Somebody of you may have touched upon molecular dynamics. Is that something which rings a bell? So molecular dynamics is you taking a system of billions of particles, like hydrogen, a gas of hydrogen molecules, and then extract all the quantum mechanics and parameterize that in the terms of a classical potential, where the particles interact. And then you solve Newtonian mechanics. That means you solve Newton's equations with a potential where you've frozen out all the quantum mechanics. So then the degrees of freedom are fully classical, and the quantum mechanics is just hidden in your parameterization of an effective potential. That's molecular dynamics in essence. And that's the way you will treat a gas with many particles. And typically then you're interested in doing some thermodynamics, and then you can actually do thermodynamics with a classical object. That's an approximation you've made, and you've frozen out all the quantum mechanics. But at a certain point, you may actually need quantum mechanical reactions. And then you have to dive deeper and do an atomistic calculation, which then is much more expensive. So science in general is about you finding the effective degrees of freedom. The problem often is that we don't have a clean mathematical recipe which links one effective degree of freedom with another one. So if you do molecular dynamics, you don't have a clean mathematical recipe which links a classical method with the basic quantum mechanics. So this is a very interesting research topic by itself. So we are going to deal with things. If you think of this lecture here, we are going to remind you of some of these quantities. This is actually both today and tomorrow. We're going to look at ansatz for the wave functions. You're going to encounter, this is actually later, we are going to deal with something which is called second quantization. That gives you the impression that there is a first and third and fourth quantization. This is just a bad name, but it's stuck with the literature. So I normally used to call it the number representation. Or if you want to, it's also called Fock space representation. Fock with an O. It was a Russian mathematical physicist. And first quantization is often referred to what you guys have seen before, like when you've been solving quantum mechanical problems with all the degrees of freedom, the spatial degrees of freedom. So typically in second quantization, you actually freeze out the spatial degrees of freedom. And these are quantities you would look up in tables of matrix, what we call matrix elements, which are integrals. We're coming back to that. And then there is a lot of small things here which link a little bit later, which we will not cover in detail, but which are also important for quantum computing. So in quantum computing, you actually rewrite the Hamiltonian in terms of Pauli matrices. And that's why you need this kind of transformation, the Jordan-Wigner transformation. So, but these are technicalities. So if you think of the topics, and this is one of the things I would like to discuss a little bit more during the break, because I want to hear about what are your scientific interests. But these have been typically the topics which we have covered in the semester. So we have something which is called full configuration interaction theory, which is basically you being able to set up what's called a Hamiltonian matrix, diagonalize that one, and then you have all eigenpairs. That means eigenstates and eigenfunctions. If you can do that, and if that describes the signs of your system, then you're done. However, when you diagonalize, the most efficient algorithms nowadays allow you to diagonalize by iterative methods, matrices of the size of 10 to the 10th times 10 to the 10th. That's roughly the limit. Now, your Hilbert space is normally infinitely large. So you have to truncate. And again, you have to have effective degrees of freedom. So that means that even if you get all the eigenpairs you are looking after, this is very much limited to the effective degrees of freedom you have. And they may not be sufficient to describe the physical system. Then we have the whole plethora of mean field approaches. So mean field is essentially us taking a complicated many-particle problem and reducing that to single particle equations, which are modified by the presence of the other particles. But in essence, it's a single particle problem with a modified field. So you can think of when you take the electrons in an electron in the hydrogen atom, this is one of the few problems you can solve analytically. It's a one particle problem. We have an electron which feels the attraction from the atomic nucleus, hydrogen, one proton, and we can solve that analytically. And this is something you did in previous quantum mechanics courses. I guess everybody has seen that, the solution of the hydrogen atom. Okay, but this is a problem you can solve analytically. Have you seen, for instance, the solution of the harmonic oscillator problem? This is also not, but we are going to remind you of that. This is a classical problem you can solve analytically. And that is extremely important because then you can make modifications of that where you modify it instead of just having a particle moving in an external potential, which you can solve analytically. You then modify that by the presence of the other particles. So you say that the particle sees an external potential which traps you, and then it sees a field which is set up by the other particles, which modifies your motion. So if you were not here, I could obviously run around the room here unhindered. But since you guys are here, I cannot do as I want, okay? That's a typical example of how my motion would be modified by your presence. And in essence, a mean field is doing something like that. Then, based on that one, you often prepare a better basis. So basis is a word I'm going to use again and again. And you can use many-body perturbation theory. We have something which is, so this course has often been taken by people from who do nuclear physics, quantum chemistry, and this is a kind of state-of-the-art method. But I know that there may also be interest in Green's functions theories, etc. So this is something I wanted to discuss with you guys, because we can always change a little bit towards the end of the semester. So this is roughly what we have. It's the these are the textbooks, and you will get these weekly reading assignments and lecture notes with programs and exercises. Yeah, you've seen this before. And we don't make any difference between the PhD variant and the Master of Science variant. You're supposed to do so, but I mean, it's, I don't care. So just a little bit about notation. So on my whiteboard, since my handwriting is not very good with boldface symbols, I will put vector signs on vectors. But in general, in my notes, this is the way you will see it. And the index counting starts typically at 0, because that aligns with the way you write index arrays in Python and C++. Yeah, these are just some symbols which you probably have seen many, many times. And I just wanted to repeat some of these things before we dive into the whiteboard. So the kind of notation, when you say a vector, this is actually what we mean. The transpose is that one. And obviously, we are going to deal with complex vectors. So when we deal with quantum mechanics, and I should also say that we are going to deal with emission quantum mechanics. That means that it's a theory which is better tailored to clean unitary transformations and bound systems. If you have a coupling to the continuum or so-called systems where you can leak particles out of the system, then you would often have to deal with what's called non-Hermitian quantum mechanics. This is not covered here. So we will stay with a standard recipe where we have Hermitian functions, and that means obviously that all our guys are complex guys. So this is the standard notation, and if you're taking a course in linear algebra, it's the way you would see it. I just wanted to remind you of some basic quantities here. A quantity which we are going to use again and again is actually the outer product, and you're going to see examples of that pretty soon. So this is just a quick reminder about some basic linear algebra, and the reason for that is that there's something we are going to use quite often, and these are called projection operators and density matrices. And then we need to remind ourselves about what an outer product is. Yeah, this is just the type of operations. I'm going to skip some of these. Sometimes I will write a matrix. So these are vectors. So these are the vector components. Every column is then just given by a vector here. Yeah, I'm not going to go through all this. This is just meant as a kind of summary. One thing we can do now as a kind of a way to break a little bit is to introduce some famous matrices. And these are matrices which we will be using here as well, but they are more important if you do a course in quantum computing. Because in quantum computing and quantum technologies, you would rewrite gates, the operation of a gate, which is actually a physical operation on a system, in terms of rotation matrices, which involve these matrices. So this is just an aside, but we are going to meet these kind of matrices again and again. And the question then to you guys is, which one of these are Hermitian, which are unitary, and which are both? And what does both imply for the eigenvalues? Should we take about 3 minutes? You can just chat with your neighbor. You don't need to present the answer here, but just chat with your neighbor. And then on the next slide, you will see the answer. So should we do a 3 minute, just stop a little bit and then take a look at these exercises? I'm going to stop the recording in the meantime. Back the recording. So if you then look at it, so sigma x is a real symmetric. So that means it's Hermitian. And you see also, this also has a very interesting property. So when I take the Hermitian conjugate, multiply with the matrix, it's actually equal to the identity matrix. So that's a definition of unitary. So this matrix is also real symmetric, it's Hermitian, and it's unitary. This other matrix here has a diagonal, so the Hermitian conjugate, and that's different from S, and it's actually not Hermitian, but it is unitary. So the reason why I bring up this with unitarity is important because essentially what we're going to deal with is to find approximations to unitary transformations which we don't know. In essence, this is what the different many-body methods deal with. So if the matrix is Hermitian, then you have real eigenvalues. If it's unitary, the eigenvalues have modulus 1. This is something we are going to utilize when we discuss with Hartree-Fock theory, because that leads to some interesting, deeper insights about the theory. If one just keeps this kind of simple linear algebra messages, and both at 1 forces eigenvalues plus minus 1, and hence it's equal to 1, is called involutory. And sigma x and h, this is called actually in quantum computing, it's called the Hadamard matrix. And it's an important gate in quantum technologies, which you can realize. So quantum technology is something which we will not discuss much here, because here we are going to simulate a physical system by solving equations, either by paper and pencil or on a computer. When you do quantum computing, you solve a physical set of equations or set of equations by rigging a physical system and using a physical system to find the solution for it. That's very different. That's what makes quantum technology and quantum computing to me extremely interesting, because you need to understand how to manipulate a complicated many-particle system in order to solve equations on a quantum computer. And that's why this step, where we solve equations by paper and pencil or by writing a computer program, this is something which gives us a quite good insight about the physical systems. And then that tells us how we can actually deal with these systems in connection with quantum technologies. So I don't know if you see the reach of these statements, but it's actually a fundamental set of important statements about quantum technologies. Understanding how you can simulate these systems, either by paper and pencil, how you can understand them, is essential in order for actually running computations on a quantum computer. So there you actually manipulate physical systems to solve, let's say, linear algebra equations. That's pretty neat. But this is not the topic here. Okay? So for those of you who are not too familiar with physics, I'm going to introduce another notation, and this is after Dirac, the bracket notation, which many of you are familiar with. So instead of writing the vector like this, I'm going to use it write it like that. But that means exactly the same. So as a vector is just a column vector. It means that the conjugate here is given by the conjugated transpose. Sometimes I just say the Hermitian conjugate or just plain laziness. And this is given by the transpose of the vector, and I've complex conjugated all the variables. And the inner product, the inner product of two vectors is just given by that. So this is just a quick reminder. So it looks like a standard inner product, except that we use another notation. So for those of you not too familiar with quantum mechanics, this is a notation which I would use, the so-called Dirac bracket notation. So just another way of writing it. So you could say that this is a physicist's approach to get into the annals of mathematics with a different notation. And there are some examples here where you can play around a little bit. So I just invite you to take a look at it. And there's an important rule here. When you look at the complex conjugation, this is something which we will use repeatedly. And this is the kind of reminder of some basic quantum mechanical aspects. The outer product, which we mentioned earlier, will now be written instead of X times Y transpose, is now written in this Dirac bracket notation. And this is what it turns out to be. So now we're going to quickly soon to look at the, switch over to the whiteboard. And we are going to discuss a little bit more about computational basis states and other topics. And this is, you will find much of the same things in the slides, but I prefer to slow down the pace a little bit, because if I see too many slides, you lost my attention. Okay, so I'm going to switch over to the whiteboard, and let's do that. So let's stop that sharing and then switch. Okay. So let's use the last 5 minutes to introduce some of the basic concepts which we are going to deal with throughout the semester. So what we want to solve now is an equation where we have what we call a Hamiltonian operator. And I'm going to label this, so this, since this is an operator, it contains kinetic energy operators, it contains potential energies, etc. So I'm going to put a hat on it to indicate that that is an operator. And I'm going to split this into two parts. One which I will call an H0, and one which I'm going to call an H of I. So this one is now assumed to be something which we can solve. It's often translated into what we call a non-interacting part of the Hamiltonian. So I'm going to say a little bit about what this means, non-interacting. Part. And this is often a type of problem which gives a good approximation to the physics or the science we want to look at. And it can even, if you're really lucky, it can be solved analytically. So we have analytical solutions. So it's an approximation to the physical system. So write it as an approximation. It's not the full thing. And can be solved if we're lucky. So I will come back to what it means by solving analytically. The other part here is the interesting one. So this is actually what we call I for interaction. So this is the interacting part. This is where two particles can interact, like if you have the celestial two-body problem, you have Newton's law of gravitation. If you think of two electrons, you would have the Coulomb interaction between the electrons. They all scale as 1 over the relative distance. The non-interacting part is normally given by the kinetic energy and an external potential, which, for instance, traps the particle. So if you think of something like a potential you can set up in a semiconductor. So suppose this potential looks like this. I'm just plotting it. And many of you have seen the box potential. And you can think of trapping the particle in here. So this potential then has a function. I'm just writing this very schematic. And I call this external. So this is an external potential which is applied to the system. So you could set up some electric fields in a semiconductor between layers in semiconductors and trap electrons there. So that's a typical example. And then, so this non-interacting part often contains that part, plus kinetic energy. Now, these two quantities are also quantities which we call additive, because if you think of the kinetic energy, if we were to calculate the kinetic energy of all of us here, we would simply add the individual kinetic energies. So that becomes additive. And it's a one particle problem, right? Because we are not interacting. So if there was no interaction, your kinetic energy would not be modified by me, for instance, blocking the door, so hindering you to leave the room, right? If this gets too boring. So that's the part which can be solved normally exactly. If you think of potentials like the harmonic oscillator or the hydrogen atom, this is a typical example. Now, the interaction part is normally given by a two-body or more complicated interactions. So this is normally given by two-body interactions, and this is two-body or higher body interactions. So bodies are not corpses here. These are objects, particles in our case. So higher body interactions. And this is normally the part which cannot be solved analytically. We can solve it with approximations, and some of these approximations can be solved analytically, but many of these have to be solved numerically. And this is a kind of a tour which we are going to do through this semester. So this means that if we can solve this problem, there's going to be a equation which allows us to find the solution. And I'm going to write this operator H, and this is a state psi, and the uppercase letter means that this is a many particle state. But if you see a lowercase letter, this is normally connected to a single particle state. And if I don't say anything, it can be single particle or many particle states, okay? But this is in general the problem we want to solve. And when I use the letter psi, I will refer to the exact solution. So before we take a break, I just wanted to bring in that normally this H0, which I said is a case which we can solve. So sometimes we can solve it, and it's normally given in terms of one particle operators, and the energy is really additive. Then we have a state. So this is a problem we can solve, and I'm going to write this as an epsilon of phi j. This system which you see here, this is the exact one. This is the one we want to solve. This means that if I take this H times phi j, this is not equal to EJ, of phi j. Okay. And after the break, we are going to remind you of what's called, or what is an orthonormal basis, ONB. And we are going to expand this object here in terms of this basis, because this is going to give us an infinite basis, which normally is orthogonal. It's often normalized. And then when we have such a basis, we can expand any other functions in that basis. And these expansion coefficients are those which many body physics actually deal with. Different approximations to finding the expansion coefficients, which will be the elements of a unitary transformation. But we're going to set up the equations after the break, okay? So I hope this kind of linear algebra stuff is something which allows everybody to remember some of the basic things. So during the break, if you want to stretch legs, you can do that. But we have Cecilia there, who's going to be the other person teaching this course. And I thought if you want to, we could chat a little bit about what things you're interested in and what you would like to do. Or if you don't want to do that and just want to stretch legs, feel free to do that. I'm going to stop the recording. Yeah? So before the break, we started with these equations. And the kind of notation I'm going to use is a letter psi. If it's an uppercase letter, it will normally refer to a Mani particle, or when we say Mani, it's two free Mani. So two body is also Mani body, although many people will call it a few body problem. The phi letter is something which I will reserve for the solution of the non-interacting problem. So this is often something which we can solve analytically. And I will show you some examples of systems where we have analytical solutions and which are often used as approximations to a more complicated interacting problem. So as in real life, interactions are the complicated things, right? If we all been individuals or independent and identical objects which didn't interact, everything would be very simple. But then the interactions among humans is what makes life interesting. And the same is with many-body physics. Okay, so let's now just proceed a little bit. So we said that this Tate phi is a known solution. And this is normally something which we can say that this phi j is a so-called ONB basis. So ONB, you will see this again and again. Yeah. Oh, didn't it react? So my pen here, so it doesn't show it on the screen. Eh? Strange. Okay, let me do one thing here. So sorry for this. So this phi of j is an orthogonal and normalized basis. That's a typical assumption which we make of it, and it's normally composed of an infinite set of solutions. So what this means is that this phi j, when I take the overlap here between these two vectors, this just gives a Kronecker delta ij here. So that's a basic assumption which we make. And then since this is a complete orthogonal normalized basis, we can then expand this psi of I in this basis. In principle, this basis, if you think of like the harmonic oscillator, for those of you who have studied quantum mechanics, this is an infinite basis of bound states. That's the harmonic oscillator. The same applies to the hydrogen atom. So it's an infinite bound basis. I'll come back to what I mean with that. This means that I can now expand this in terms of these other functions, and we have these overlap coefficients. And these are the coefficients of a unitary transformation. So theseCij's are the elements, the matrix elements of a unitary matrix, because this is going to represent a unitary transformation. So you've probably seen this before, and technically theseCij's are then given by the overlaps between the psi of I and one of these states phi j here, which we have selected. And so what we can say then is this is normally called a wave function based approach. And the sum in what we have here, this j equals 0, goes in principle to infinity. So we have theCij's and phi j. Let me just rewrite it. So these coefficients,Cij's, are the matrix elements of a unitary transformation, of a unitary matrix. Of a unitary matrix which I'm I'm just going to call C. So just to remind you quickly of that, a unitary matrix is a matrix which, when we multiply it with a Hermitian conjugate, it gives us back the identity matrix. And the C Hermitian conjugate is equal to the inverse of that matrix. So this is a kind of matrix which we are going to see again and again. And the thing I wanted to say something now is that this truncation which you have, or this is equation which you have from j equals 0 to infinity of Cij of phi j, is something which we are going to approximate with a finite dimension. So that will give us what we call an effective Hilbert space. Sometimes we don't have a recipe, except that we can look at the energies and see if the energy stabilizes as a size of the effective Hilbert space. Other times we can actually make clear mathematical transformations from an infinite basis to a smaller basis. But what we are going to do in practice is that our equations will be approximated where this D is a finite dimension of the system. And that means that the matrix which we are interested in, this Cij matrix elements, they are then this matrix is going to be a finite matrix. So D is a dimension of an effective Hilbert space. So it means that we have to make truncations. So it means that this matrix C is going to be a complex matrix, and it's going to have dimension D times D. If we can set up a problem like a diagonalization problem, where we then can diagonalize, then the eigenvectors will give you those coefficients Cij. So we can write this vector Ci here in terms of the general vector, which now contains all the states which we're looking at. So these are the D states. And that will simply now be given by this unitary transformation, like that. So now I've skipped the subscripts because I just made a vector psi, which contains all the solutions. And that is then given by this matrix multiplied with the previous solution. So what you could say, this deals with what we normally call wave function based approaches, because we have a set of wave functions or set of states. And we use that to approximate the exact solution. And that means that many-body methods like many-body perturbation theory, Hartree-Fock theory, Copper cluster theory, Green's function theories, just name one of them, what they do is to try to approximate Cij. So, and this is the reason why we are going to use sometimes simpler systems, which we can diagonalize exactly. When we can diagonalize exactly, which means exactly numerically, because you have Abel-Ruffini's impossibility theorem. Does anyone, have you heard of that? So that simply states that if you have a fifth order, high order polynomial, you cannot find the roots of that polynomial with rational numbers. But you can solve it numerically exactly by diagonalization algorithms. But you cannot find an analytical solution to that problem. So a eigenvalue problem translates into you finding the roots of a given polynomial. I don't know if you remember that from linear algebra. We have something which you call the characteristic polynomial if you set up the determinant which you want to solve to find the eigenvalues. That gives you a characteristic polynomial, and then you want the roots of the characteristic polynomial. And then Abel and Ruffini's theorem simply states that you cannot find a solution in terms of rational numbers beyond a fifth order polynomial. There are cases which you can solve analytically. And in many-body physics, you will see in chapter 4 of the textbook, there are cases which we can solve at least by exact diagonalization, and even cases where we can find analytical solution. These cases are invaluable because we can test all the approximations against exact solutions. So when you typically develop a many-body method, you want to have test cases where you have exact solutions. So with exact, I will often mean numerically exact. So when you diagonalize a problem, you can find the solutions exactly, but numerically. So in a nutshell, this course actually deals with us trying to find approximations to this guy here. So it sounds a little bit strange. I mean, is it that simple? So I wanted then to say a little bit about this kind of many-body basis by looking at a simple system. And that gives also a connection to quantum computing. And I will say a little bit about that. So what we're going to look at now, just to understand a little bit better some of these concepts, is to look at a two-level system. This could be one particle in a harmonic oscillator trap. But what we are doing now is simply to idealize this system with a state epsilon 0 and a state epsilon 1. And we are assuming now that these states, so there's no interaction now, and we are assuming that these states here, they have as a solution a phi 0. So we haven't specified whether this is one particle or many particles, but these solutions are now given to us. It could be something like a spin system. So we have just a two-level system. This is all what exists. Like that. So this is this non-interacting part of the Hamiltonian, which we now assume can be solved exactly. Then we can add some interaction afterwards. But if we now have these two solutions, we could now think of these as spin systems. So what we could think of now is that this phi 1 is given by a simple vector, which could then be a system which now represents a spin-up state. And this could be a spin-down state, just to couple this to something which you may have seen before. And then this phi 0 is given by 1, 0. This is what we would call an orthogonal and normalized basis. So if you take phi 0 and multiply that with phi 1, which in this case is simply 1, 0 as vectors, multiply with 0, 1, you see that this is equal to 0. And then if you take phi 1 with phi 1, you get 1, and phi 0 with phi 0, you get 1. Now, what we could think of now is that there is also an interaction piece, which we haven't defined. And when we apply the full Hamiltonian, we're actually getting a problem like this, of not phi, but psi, of psi 0. And so I'm just stating it like this, and psi 1. Okay? Now, what happens when we look at this now, if we use this as a basis, as our computational basis, this is actually what we are going to use. So I call this an orthogonal and normalized basis, but I wanted to emphasize a kind of wording which I'm going to use. So this is going to be our computational basis. So since this is a computational basis, what we can do now is to expand this specific state, which we have here, or that state, in terms of that basis. So that means that we would then find that psi 0 is now given by some constant. This is a complex constant, multiplied with phi 0, plus some beta multiplied with phi 1. This is the same as this C00 element, which we set up before. And this is the same as this C01. So these are the unknown matrix elements, which we would need to find by some recipe. And in this case, if we have two states, this will lead to a 2x2 matrix. And we know that that leads to a second order problem, which we can solve analytically by paper and pencil. So that's a pretty trivial case. So we can diagonalize this problem, because then the full problem would simply be us setting up the determinant of the Hamiltonian as a matrix minus lambda times I and put that to 0. And since we only have 2 states, this translates into a 2 by 2 matrix. We are coming back to this in exercises next week. So you will see this in explicitly in an exercise next week. And then we would find that this psi1 is then given by some gamma times phi 0 plus some delta times phi 1. And this would obviously be the coefficient C10, and this is the coefficient C11. So if we can solve the problem by diagonalization, we would find these coefficients without any problems. Now, there's a reason why I actually bring up this 2-level system. So this is something which relates to quantum computing, since quite many of you are interested in quantum technologies. What we could say now is that this state represents bit 0. And this is bit 1. And we would just call this qubits. So that means that this physical state of the system now is given by a qubit 1, a qubit 0. So we would encode information instead of having bits in a standard computer. We're actually looking at physical systems, which we then can manipulate by, let's say, a laser. So we could now have, suppose the system in the initial time, t0, is in this state here. Then by some kind of magic, we could promote it up to this state, which in this case means flipping the spin. And then we would have flipped the system from bit 0 to bit 1. Now, the reason why I'm bringing this in is that this also brings in the basic concepts which we're going to deal with here. So we need a basis. And in quantum technologies, you have different platforms for making quantum gates. And the hunt for the platforms is actually to find systems which have physical states which you can manipulate long enough. That's a big quest. And that's why it's so important to understand the physics of many body systems, because that allows you to find systems. So like we have an experimental activity where they're looking at something which is called point defects in silicon carbide in semiconductors. And what they are desperately looking after are systems like this, where you can identify this state and that state, and then manipulate that over time. So quantum computing is actually you manipulating physical systems and hoping that these systems live long enough that you can do meaningful operations. In a nutshell. For us, on the other hand, technically here, this is a basis. So I'm bringing in all this kind of physics jargon so that you see where this can lead. But at the same time, now we want you to focus on the mathematics, which is just the basis of the system. Okay? So if you now have these specific states here, what I can do now is to introduce some technicalities, which we are going to use again and again. And now comes the completeness relation, which many of you probably have seen before. And in our case, we would now sum the outer products of this computational basis. So that means that we would have a sum from I equals 0 up to 1, because we only have 2 states. And then we would have a phi of I, and this is the outer product of the states. If I do the math here, if I write these 2 matrices, if I take these 2 vectors, which I have defined here, so these are the 2 guys, you take the outer product of these, and if you do the outer products of these 2 guys, you will see that this gives you the identity matrix. And I'm going to show you that explicitly on the next page. So this is what we want. If you do the outer product, so let's just wait a little bit so everybody has time to write down. It's so easy to flip pages on the whiteboard while you guys are just desperately trying to write down. Now the PDF file, I upload the PDF file of these slides after every lecture. So in case you missed something or you were in doubt about my ugly handwriting, then hopefully you can look it up again. So if I do this now, what you will get is 2 matrices, 1, 0, 0, which is actually this outer product. So just to remind those of you who come from a non-physics background, as vectors, this will be phi 0 vector and phi 0 transposed vector. This is exactly the same what's written there. And the other one, which is phi 1, is just 0, 0, 1. And you can see that when you do the math, because what you have then is just a vector like this, 1, 0, 1. And then you take the outer product with 0, 1. That's essentially. I hope you don't get offended if I go through this kind of linear algebra. Now, this allows me now to introduce two very important operators, which we are going to see again and again and again. Yeah?
Is there a reason why you're like switching between the uppercase and the lowercase?
Oh, these ones? Yeah, this is just bad writing. So this is, yeah, it's the same. Yeah, I should put it like this. Sorry. This is just my hand. Sometimes you forget. Thanks. If something is unclear, never hesitate to ask. Okay? So we can now define an operator P, and this is given by phi 0. This is the outer product, phi 0, and an operator which I'm going to call Q, and I will actually use this notation for the rest of the semester. These operators are interesting. One, and I leave that to you to prove, but you can see that quickly, P squared is equal to P. And the same applies with Q squared. Furthermore, if I take the standard commutation between these two matrices, which is equal to P times Q minus Q times P, this is equal to 0. If I multiply P with Q, this is also equal to 0. Does anyone remember what these kind of operators are called when P squared is equal to itself? Yeah? Yes. So this is extremely important for us because we are going to use, when this acts on a state, it's going to project out only some specific states. It's essential in quantum computing when you think of measurements, because when you make a measurement, the system collapses. So what we have previously here, in this state here, this is a standard quantum mechanical superposition, which you also have classically. So superposition is not something which applies to quantum mechanics only. If you think of Fourier series, you have a superposition of cosine and sine waves. So it's basically the same mathematics. But this is a quantum mechanical superposition, and the state can be in several, you can actually access many more states than you can do classically. But when you make a measurement, it collapses to one of them. So these are also called idempotent operators. So to see that this is a projection operator, you can just now apply it to one of these states. So P and Q are what we call projection operators. And they are very important because you can, in some cases, you can actually formally link an infinite Hilbert space through projection operators to an effective smaller Hilbert space. And you can do the math exactly. But in most cases, you would have to do an approximation. So these are projection operators. And you will see immediately that if we act on the state, suppose we take this state psi 0, and I act with this one on psi 0, which we defined earlier. This is the same as if I just write the algebra, it's 1, 0, 0. And then it's multiplied with this parameter, this complex variable, times 1, 0, plus beta times 0, 1. And when we do the algebra here, what we get is alpha times 1, 0, which is the same as alpha multiplied with phi 0. So this projects out one of the states here. And if I take Q on the same, on psi 0, it shouldn't come as a surprise that this is equal to beta times phi 1. Okay, so you're going to see, I'm just introducing it here now because we're going to use these quantities again and again here. Now, what I'm going to do now is also to sneak in another technicality, and this is the tensor product. Actually, when we write a quantum mechanical state in a compact way, what lies behind it is a tensor product. And this is something which is easy to forget, very easy to forget. The reason why I bring it up is also that because that brings in the kind of notation. So I'm going now to look at two systems. So instead of this system which you have here, an isolated one, we can think of two isolated ones which could also interact. And then you can see how you can use this basis which we had here to make a two-body basis, a computational basis which is going to be orthogonal, normalized, and will serve as a computational basis. Okay? So if I want to make, in quantum computing, so I'm using this a lot of as examples, we have something which is called 2-qubit gates. So you can actually rephrase many of the algorithms, like Grover's algorithm, in terms of 1-qubit gates. So the system which you see here is a system which can be used to make a 1-qubit gate. So you act on 1 qubit if this state is bit 0 and this state bit 1. The next type of gates which are important are 2-qubit gates. And then we are looking after systems where we ideally would have two isolated systems which can be treated as distinct, which interact with each other. So what we could think of now is a new case. So we are going to look at a we could call it two-particle or two-body computational basis. So let me just write this down here. And this is probably the last thing, computational basis. So I'm putting quotation marks here because this doesn't need to be a two-particle. Every one of the systems could be complicated many-particle systems. And when you want to realize many of these qubit systems, they are often complicated many-particle systems. So what we could have now is this non-interacting case where we have system A. And in that case, we will have a state 1, 0, which we use to label that. So that's the way we now label it in terms of the two vectors. So this could be qubit 0 in system A. And then system A has an excited state here, which we call for still system A. And this will be 0, 1 system A. And then we would have the same here, but we label everything with B. So this is just another physical system which can be realized. And then we have the same here, 1, 0 of system B and 0, 1 of system B. So what's the physical analog of this kind of system? This is just a simple, how to say, abstract system, but the physical analog would be what we call quantum dots. So you can actually make such kind of small traps which trap a single electron, which say spin up here and spin up here. These wells are harmonic oscillator lookalikes. And we could think of this as system A and system B. This is actually what is made in the labs. If you look at quantum dot semiconductor quantum computers, where you can actually isolate single electrons in small regions in space. And the states, the low-lying states, can then be identified as bit 0, bit 1, etc. So this is a physical realization of this kind of system. Now, what we want to do now is to define the computational basis for this system. So without any interactions. And we simply assume that these states exist, we have found them, and we label them mathematically with these states. So this is a choice of ours, right? So if you do that, we can now make a system which I'm going to call phi 0 of system A and B. So this is a non-interacting case. And I can construct a computational basis now of system 0, that state, and it's a tensor product. So I use this to bring in the tensor product notation. And this is the same as ours. And now I skip the subscripts A and B. I hope it's okay. And thus it's simply given by this one. And this is our new state, 1, 0, 0, 0. Okay. Now we have assumed that there is no interaction. So the hope is that if I take this non-interacting part of the Hamiltonian and multiply it with that state, I0, AB, I get something which I could call E0, AB. This is the two object system of AB. So that means that this state is now a state which is the solution to this interacting piece, which is now the interaction, not the interaction, but the non-interacting Hamiltonian for these two systems. Now, this state, which I have here, is something you will often see written, and this is the kind of notation which we're going to use. If you look at this notation here, when you have many such states, it gets boring to write the tensor product sign. But what you would often do is to write it in a compact way, qubit 0 or state 0 and state 0, like that. Now, this is also cumbersome because what you could do is actually to label this as your first state. Because at the end, when you do the computations, you want to make a table. And if I then go to number 0, this points to 0, 0. And I know exactly what kind of state I am in then. So, and you can see now, if I look at this one, I could write this as x0, x1. And I can write a recipe where I take 2 times x0 plus x1. And you see now that if this is 0 and this is 0, that gives 0. That's that state. So that's a simple formula which is actually used classically for bit encoding. And that gives me a very simple way when I tabulate this one in a computer, because at the end, when you have many such states, you have to make a table. So my table starts with 0, and I know that number 0 points to these two dudes. Then if I take the next one, I can now, since I got a little bit excited, I can now think of a new state, which I'm going to put a label 1 on, AB. And this is going to be phi 0, the one we had previously, exactly the same, but the tensor product with phi 1 in system B. This is the same as 1, 0, tensor product with 0, 1. And that gives me the following vector, 0, 1, 0, 0, which I will label as the state 0, 1, which is a compact way of labeling the state. Now, this is also going to be state 1 if I use as recipe 2x0 plus x1, because that's equal to 1. So you have 0 plus 1. Then when we get more excited and we see that we can actually continue, if I do that, that is going to be given by 0, 1, tensor product with 1, 0. That gives me 0, 0, 1, 0, which I will rewrite as 1, 0, which again, when I use this simple formula, which I have here, this one, in order to label the state, this just becomes my third state, or just state 2 here, when you start with 0. Finally, I can then set up the state 1, 1, which is simply going to be the tensor product of 0, 1, system A, 0, 1, system B, and that is, and this is not coming as a surprise, 0, 0, 1, which would also be equal to state 3, because then I have 2x0 plus 1, this is 1, this is 1, and that gives me 3. So then I have a mapping with these kind of bits, which now simply tells me that if I have number 3, this is the state the system is in. Now, you can quickly see that if I take these states, you will see that they are orthonormal to each other. And it's not that difficult to prove that these four states form an orthonormal basis. So I can use that as a computational basis. And that if you just try 0, 0 with 0, 1, it's pretty easy to see that this is going to be equal to what normal. Actually, I cannot use this joke anymore because I used to see the number of points which Norway would get when they try to qualify for the World Cup. But I can't use that joke anymore. It was depressing to watch them qualify in the 70s and 80s because they would never win any games. Okay, but so this is an orthogonal basis, right? So it's an ONB, and that means that if I now take the full Hamiltonian and I have a state which I want to recognize as the lowest lying state, so we put a 0 here, that could now be a linear combination of these four states. And then I would have 0, 1, plus, and then I would have a gamma, 1, 0, plus a delta of 1, 1. So this is now my computational basis. And then I can define new projection operators where I take the outer products of 0, 0 with itself, 0, 1, 1, 0, in exactly the same way as we did here with the projection operators. But now we would have a state which represents two quantum mechanical systems. Now, the reason why I stress a little bit this tensor notation here is that normally when we look at even at a single particle state, this contains spatial degrees of freedom. And if we're looking at the not spinless object, but object which have spin, it will be a tensor product with spin space as well. But we would never write the state in this kind of way here, because as soon as you add more and more objects, this is not nice to write. But then you would write a compact notation like this. And when you have many, you can compactify it to an even more compact notation, which is then handy when you want to compute. So the first lecture today was actually bringing back many of the things from linear algebra to bring in this concept of computational basis. And what we are going to do tomorrow is actually to use this in the calculations of expectations values of a two-particle system. And then we're going to use the helium atom as an example, which is something many of you may have encountered in physics courses. And that's the first case where we actually can set up an approximations to the system and run calculations and see what we get. I hope this kind of was not too boring, but I think it's important to bring in some kind of common basic concepts, which we are going to use again and again. And I like to bring in all these kind of links to different fields, especially quantum computing, because many of you are interested in that nowadays. But anything we've done here is something you can apply to any physical system. So you're not limited to a specific system. The basic language, the way you construct states as a computational basis, the whole idea is to have a computational basis which you believe is a solution to a part of the Hamiltonian. And if you're lucky and find something which has an analytical solution, you have often, how to say, a more gentle approach to complicated many-particle systems. Because some parts can actually be calculated analytically. Okay. We take a break and then back tomorrow. Yeah.
Sounds good.
Yep.